which are stably complex and have a SU structure. Roughly speaking, it's the first Chern class is 0, or equivalent to say determinant bundle, the top exterior power. Yes, is trivial. It's the line complex bundle, and it's trivial. Okay, and of course, if we have stably complex manifold and SU manifold, we can consider the Cartesian product, and so we have a natural way MSU model structure on MU. And so, in fact, one can check that this model structure is the following structure. MU is just smash product of MSU and secondary suspension of CP infinity suspension spectrum. And so one can ask, we have cohomological operations in complex cobordism, some Landweber-Novikov algebra. And we can ask which of them respect this MSU structure. So which of these cohomological operations are MSU model maps, are SU linear. Okay, what SU linear operations we have? No, for example, we have multiplications by scalars. It's SU linear. Okay. What else? No, for example, following Sergei Petrovich Novikov, using this term isomorphism between these cohomological operations, is exactly cohomological operations in MU and characteristic classes in complex cobordism theory, we can define these operations decay with the following property that on coefficients on bordism groups, it acts like, no, in this way. Decay of bordism class of manifold M is the bordism class of submanifold N dual to the direct sum of determinant bundles. For example, D1 is submanifold dual to determinant bundle, and in particular, it's SU manifold. D1 of M is SU manifold because Chern class of the dual to determinant bundle is 0. But higher operations, of course, it's not. No, they do not take values in SU manifolds. Okay, and so maybe you can ask why we are interested on the action on the homotopy groups, and it's because any cohomological operations is uniquely determined by its action coefficients for complex cobordism. So complex cobordism homological operations algebra acts faithful on coefficients groups, and moreover, it's SU linear on, also if and only if its action is SU linear on coefficients. So we do not lose a lot of information if we restrict our attention on the action homotopy groups. Okay, from the Novikov approach, you can construct some other families of SU linear operations, but in fact, you can obtain much more operations because, in fact, we have the following proposition that these operations form a topological basis of this omega module. So any SU linear operation had the following form: it's some series with coefficients, it's multiplications by scalars, and these operations, it's from the MSU model structure on the slide above, on the slide, previous slide. No, for example, if you have multi-SU linear operation in several variables, then it's just series in products of such operations, so nothing else. And of course, one can determine, one can describe the structure of composition of such two operations. If you want to describe this composition, you need to describe what is the decay of multiplication of two elements and what is composition of decay and DM, and you can do this in terms of formal group law, universal formal group law of complex cobordism. For example, we have these formulas, and this is coefficients of the kth power of formal group law, and this is coefficients of this formal group law, also related to universal formal group law. It is nth formal power. So we have the description of all SU linear operations, algebra of SU linear operations in complex cobordism. Now about C1 spherical bordism. What is it? No, stably complex manifold is C1 spherical if its determinant bundle is induced from universal bundle over CP1 eta, or equivalent to say the first Chern class is induced from generator in the second homology of CP1. So the first C1, the first Chern class is spherical. It's induced from sphere CP1. So because this name is called C1 spherical. is the definition of C1 sphericality of stably complex structure. And so the bordism theory based on such stably complex manifolds, C1 spherical stably complex manifold is the W, the C1 spherical bordism theory. It was introduced by Conner and Floyd. Okay, but we have one problem here. If we consider two C1 spherical manifolds, their Cartesian product maybe not C1 spherical. For example, CP1 squared is not C1 spherical, and also, and moreover, it's not abundant to C1 spherical one. So we have no natural canonical multiplication of this theory. But if we have SU manifold and C1 spherical manifold, its Cartesian product, their Cartesian product is C1 spherical. So we have natural MSU model. Yes, it's said we have natural MSU model structure on W. And this forgetful math, of course, is linear. And also, we have the following theorem due to also Conner and Floyd. We can describe this W as the cofiber of this map is multiplication by the generator of the first homotopy groups of MSU theta. The cofiber is exactly W. And as MSU module, it's just MSU smash the suspension of CP2. Okay. And this is MSU model description. And on the other hand, W is the direct summand of MU. MU is just wedge sum of W and forced suspension or shift of MU itself, as MSU models also. It's a theorem of Conner Floyd and I think Chernykh. So it's advantage of W with respect to MSU because from this description we have that homotopy groups of W much simpler than homotopy groups of MSU, for example. It's direct summand of complex bordism groups. And the projection on the second summand here is this operation where W is a fiber of this operation, and this operation also have very clear geometrical sense. It just sends M to bordism class of submanifold dual to this direct sum of determinant bundle and complex conjugated determinant bundle, separation delta. And so we have W is just direct summand, additive direct summand of MU, and so we have some projections on this summand. All of them have the same form. Yes, have this form 1 minus F delta, where F is right inverse to delta, to operation delta. And this projection is linear if and only if F is linear itself. The right inverse is linear. For example, Stong defined his projection in very geometrical way. It just sends M to submanifold of this product dual to eta bar tensor product with determinant. It's one of SU linear projections. For example, yes, it's a projection that it's SU linear. For example, it has this expression in terms of decay, where alpha 1k is just its coefficients, corresponding coefficients of the universal formal group law. So this nice description. And Stong used this projection to describe torsion-free part of MSU cobordism ring, coefficients of SU ring, and to define multiplication on this W to describe this torsion-free part of SU bordism ring. So any SU linear projection just defines SU bilinear multiplication on W in this way. We have two elements of C1 spherical bordism. We can multiply them on the complex cobordism. We obtain something not C1 spherical, but then we apply projection and obtain some C1 spherical bordism plus. And this is associative and commutative and unital multiplication on W, SU linear, if pi is SU linear. Okay, and maybe I need to tell here that Conner and Floyd also defined some projection. But Conner and Floyd used this theory W, which they introduced, and this projection to define torsion in SU bordism ring. And they defined another projection to calculate the ranks of torsion. And this projection is is not the same as Stonk projection. It's defined with the explicit form of 1 of right inverse for delta. But they define the same multiplication W because they have the same initial part in this expression. Okay, and in fact, we can describe all SU linear multiplications on W because we know all SU linear operations in complex cobordism, and all higher decay vanish on W, and so we obtain the following description that any SU linear multiplication on W has the following form. It's just ordinary multiplication in complex cobordism. This G is G1. It's a submanifold dual to determinant bundle, D8, DB, and some coefficients where V is some explicit complex cobordism class, and W is an arbitrary element of fourth homotopy group of W. And all of these multiplications are unital, associative, and commutative. And from the general point of view, this formula, of course, agrees with the fact that, in general, if you have a good ring spectrum, infinity ring spectrum, something like this, and an element from homotopy groups, and we consider cofiber, then of course we can define R model structure on the cofiber, and we can describe multiplications. And abstraction to the existence of R linear multiplications lies in these homotopy groups, this homotopy group, and the collection of such multiplication is the torsion for the following homotopy groups. And then in our case, it's theta from P1. Odd dimensional groups are vanish, so this abstraction group vanishes, and we have torsor for P4. K is 1, so P4 is some elements from here. And where D in this picture, D is just boundary map of this cofiber sequence, corner-folded cofiber sequence, and the following map to the second suspension of M2 is just it's more or less this. Maybe it's in fact maybe minus D, but it's more or less this thing. Okay, but also from the distribution of projections, we can obtain the following thing. No, I think the following part is about what the fourth homotopy group. No, the fourth homotopy group is just free abelian group of rank 1 generated by this bordism plus. Maybe it's not obvious why this bordism plus is C1 spherical, but it's just a Stonk projection of C1 squared. So we have only one integer parameter for all such multiplications. For Stonk multiplications, Q is 0. And we have this relation. We have generator of the second homotopy groups. Its square is 4Q plus 1 of the generator of the fourth homotopy group. And in fact, there is no other relation in the homotopy ring, in the coefficient ring of this theorem. So we have the following theorem with respect to the multiplication star Q. This ring has the following form. It's a polynomial modulo. This is the only relation, where x1 is CP1 and x2 is this generator. It's generalization of Stonk description of the ring when with respect to multiplication defined by the Stonk projection, where Q is 0, and then x squared is the x2 exactly, and we obtain the polynomial ring without second generator. And so we have this ring, and also we have another structure here. We have operation D. All higher D2, D3, and higher dk vanish on W, but D1 is not vanish, and it's kind of differential, but it does not satisfy the Leibniz rule. It satisfies the following kind of twisted Leibniz rule, and no, it's a little bit mysterious thing for me. I don't know. I don't know what does it mean. For example, if you invert prime 2, then W kind of trivialized. W is just then wedge sum of MSU and shifted MSU, and then this structure is equivalent to some involution on W with, and you have two eigenspaces +1 and -1, and it's kind of simple. But if you do not invert prime 2, no, I don't know what does it mean. I saw something like this in some surprisingly different contexts, something like this, like birational geometry and volume forms with logarithmic poles in algebraic geometry with exactly the same formula for the Bernstein ring of the corresponding birational classes of algebraic varieties. If something, I don't know, if anybody knows something about such structures, please tell me. I don't know what this means. What is the twisted Leibniz rule? In which context it may be appear? Okay, and also we can describe multiplications obtained from its linear projections. It's roughly speaking half of them. It's for if we don't leave parameters even. In terms of projection, this parameter q prime is just image of this class V. And also we can describe projections which comes from we can describe multiplications which comes from projections which commute with D, with operation D. No, commute with D is equivalent to say that pi D is D because no, for any linear projection, pi D is D, and if it's equal to dp, that's commuting relation. And this is the quarter of all multiplications. And any such projection had the following form. We can choose some one projection which satisfies this SU linear and commuting with D, for example, Stone projection. And then we obtain that any other projection has the following series form, a power series in the operation delta at the projection of the another summand, delta in the power of k. And this is some coefficients. It's wk, some elements from omega groups. So w C1 spherical bordism groups projection, and this is operation D. And why it makes sense? Because we have the following proposition for any such linear projection which commutes with D. This formula defines exotic multiplication complex bordism. We have it's associative and commutative, but not unital. And so such projections can allows us to define some exotic multiplication on complex bordism itself. Okay, now about the main part about complex orientations. W, it has problem that it has no natural multiplication, but it has some multiplication. Okay, it's fixed it, but it has the main the great advantage with respect to MSU. It's complex orientable. If we have any complex orientation of MU and any projection of MU to W, then its image is the complex orientation of W. Okay. So in fact, W is kind of the simplest extension, a complex orientable extension of MSU in the following sense. For example, it just say that the only abstraction to complex orientability of MSU is this element theta, which we kill here. For example, if we consider symplectic cobordism, then abstractions to complex orientability of symplectic cobordism is ray elements, and you need to kill all of them to obtain finally the complex orientable theory. It's exactly the abstractions to vanishing of some differentials in Atiyah-Through spectral sequence of CP infinity. No, here it's only one of this abstraction, and so we obtain a complex orientable extension of MSU. No, okay, and then we have some multiplication. We have complex orientation, so we obtain some formal group law. And what we can say about this? To say something about this formal group law, we use Buchstaber's approach. Victor Matveyevich Buchstaber studied this in the past. So, okay, W is a cofiber of this multiplication. Okay, consider the similar cofiber in the MU. It's gamma. It's cofiber of this multiplication. But theta is 0 in MU, so this gamma is just MU batch with shifted MU. No, additively, it's trivial. But we can, yes, and we have the natural map from above to the below. W to gamma is the form 1 plus D. But we can define multiplicative structure on this cofiber, multiplicative structure. No, I believe this formula is clear enough. We have polynomial, modular relation, additively is just free module of rank 2. We shift it with in degree t is in degree 2, and this formula defines your multiplication on this homology theory on this spectrum. In this notation, phi is just 1 plus td. Okay, and if we do so, we obtain the following. Yes, of course, gamma is itself of course complex orientable because it has canonical complex orientation because we have multiplicative inclusion of the mu to gamma of the first summand. This inclusion gives you the canonical orientation. You can consider orientation of mu and then its image under this inclusion. And the corresponding formal group law is just the complex cobordism formal group law, but just considered over not over omega u, but over its multiplicative extension gamma point. And but on the other hand, we have phi, and if we have some complex orientation of w, then its image is also orientation of gamma. And so we have two orientations of gamma. And then one of them is the power series in another, and we have some power series series. In fact, of explicit form, it's kind of 1 plus d because it's phi. And then no, so Buchstaber's observation is that multiplication defined in this way such that this phi is multiplicative. So we just obtain that image of our formal group law unknown is strictly isomorphic to universal formal group law, which we know, and strict isomorphism is only in principle known. So this is maybe allows us to, in principle, calculate this formal group law. No, of course, it's not very simple, but in fact, it allows us to calculate something from this formula and calculation modulo some decomposable elements. We can calculate this formal group law modulo decomposables in this ring. No, this is the formula. We have u plus v. We have this summand, and this general high order summand. Here, C1, C2, Ck is integers. They depend on complex orientation of W. X1, X2, Xk is generators of W ring. Q is parameter of multiplication. Mk is greatest common divisor of binomial coefficients. Now this formula. Okay, what we can obtain from this formula? In fact, we can obtain two bunches of applications. One bunch of applications is about a ring generated by these coefficients of this formal group law. For example, the first that we can calculate that for any multiplication and for any orientation, these coefficients of this formal group law do not generate the whole ring. So for example, for complex cobordism, they generate the whole ring, and in this situation, they do not. It would be interesting to understand what this theory W means from the perspective of formal group laws. And this theorem say that, for example, the first naive hypothesis that this is universal for formal group laws of some sorts. No, it's not universal because it's not generated by formal coefficients. No, maybe it have some another sense because no, okay, and another corollary is that we have no surjective multiplicative transformation, so we have no multiplicative projections from U to W because of this proposition. But as linear, we have a lot of them. But if we invert some primes, we have another picture. No, if we invert 2, prime 2 is kind of specific in this theory, so it's not very surprising that if we invert prime 2, then okay, these coefficients of this formal group generate the whole ring. Okay, but in fact, abstractions to the coefficients generate the whole ring leaves only in some dimensions. In fact, we cannot generate by the coefficients some generators of this quasi-polynomial ring in some dimensions. And these dimensions are related to Fermat primes. And in fact, it's true that if we invert Fermat primes greater than 3, you even do not have to invert prime 3. Then also these coefficients generate the whole ring, the whole localized ring. And no, I don't know how many of them countable or no, countable or finite number of these primes. But if we invert them, we obtain the thing, and maybe this means something from the also from the formal group law perspective and number theory perspective. Maybe it seems that it means something. I don't know. No, it's sigma primes. What does it mean? Okay, and another application is that if we have formal group law and the ring which we understand, we can ask if it Landweber exact. We have the classical Landweber theorem that if you have formal group law and if it's Landweber exact, so some coefficients of this formal power form a regular sequence in the your ring, then this standard product is also homology theory. And if your formal group law comes from some homology theory, then it's this homology theory itself and Fock homology also. And from some other calculations with this formal group law, we can obtain that for any linear multiplication, this W is Landweber exact. So it can be obtained from the mu by the change of scalars. And for homology also, because, of course, for homology and multiplicative theories. No, okay. I think it's all what I have. It's some cited papers and some papers, my papers on the subject. And thank you for attention.